Hi, everyone. I hope you're all doing well, staying healthy, staying inside, getting your schoolwork done. I know I've been telling you I was going to make a video and I've kind of been slacking on it, but trust me, I've been really busy around here. So today we're going to talk about limiting reactants. Now, just so everybody recalls, I'm going to give you a little refresher on stoichiometry. Limiting reactants is just an extension of stoichiometry. So just to refresh your memories, we talked about two different types of conversion factors that you'll be using in all of these calculations, and it's still the same for limiting and excess reactants. You're still going to be using your mole ratios to convert one substance into another substance. Those come from your balanced chemical equation, and you're still going to be using your molar mass to convert the mass of something into moles or the moles of something into mass. Sorry about that. Technical difficulties with zippers. All right, that's my life. So anyway, molar mass, mole ratio, those are the two conversion factors you're going to be using for all of your calculations. And you can see these are the class notes that I posted on Google Classroom that you also all received during class before we left for the chaos. So again, just a refresher, here is the roadmap that we've been using, substance A to substance B. So we can start with mass, we can start with moles, but you're always starting with substance A, and we can end in mass, we can end in moles, but you're always ending with substance B. And those are the conversion factors you would use to get from A to B. Okay, now here is an example of a conversion from moles of one substance into moles of another. So you have moles of CO2 given to you in the problem. You're asked to find moles of lithium hydroxide. The balanced equation is there, and the conversion is set up using a mole ratio because we're starting with moles, we're ending with moles. So we're just using a mole ratio to get from our starting point to our ending point. And then here we have mass and moles combined. So we're starting with moles of one substance, we're converting it to moles of something else, and then converting that mole value into mass. So we're given 3 moles of water to start with, and we're asked to find mass of glucose. And so that requires us to use first a mole ratio step and then a molar mass to convert moles to grams. Okay, and here we have just sort of the opposite setup. We're starting with mass and we're asked to find moles of something else. So you start with the mass that you're given, and then you convert grams to moles using a molar mass and then a mole ratio from your balanced equation to convert that into moles of something else. Anytime you're converting into something else, you're going to be using that mole ratio step. Anytime you're converting grams to moles or moles to grams, you're using that molar mass from the periodic table. So finally, here's an example of mass of one thing to mass of another thing. We're starting with mass of hydrofluoric acid in this case, and we're ending in mass of tin fluoride. So we start with a molar mass step, then we go to our mole ratio step, and then another molar mass step to end in grams of SnF2. Okay, on to the new stuff now. I'll spend a little bit more time talking about this. Limiting reactants. So basically, if you think about this like you are baking something or cooking something, it helps a little bit to understand what a limiting reactant is. And that kind of ties right into the trail mix activity that I'm having you guys do this week. So in a reaction, generally one reactant is used up before the other. There's really not too many times where you're going to have the perfect amount of all of your reactants to create some amount of product. Usually you have enough of one reactant to make so much product, but then you have some of the other reactant left over at the end. So if you think about it like you are, let's say, making pancakes. I use a pancake recipe that calls for 1 1/4 cups of flour, and it calls for 1 egg, and it calls for a cup of milk, and it calls for a tablespoon of baking powder and a tablespoon of sugar. And so like, let's say I want to make as many pancakes as I can with the ingredients that I have. And I only have 1 1/4 cups of flour, but I have like endless amounts of all the other stuff. I can only make one batch of pancakes because that is the ingredient that limits the amount of product that I can form. I can have as much of the other stuff as I could possibly have, but it's not going to allow me to make any more pancakes because I've run out of flour. So that would be your limiting reactant in that case. The excess reactant, those are the reactants that are not used up during the reaction. You're going to have some of those left over at the end. So the limiting reactant determines how much that you can possibly form. You can't make more stuff than the limiting reactant allows. So even if you could potentially make more with the excess reactant that you have available, the limiting reactant will limit what you can possibly form, even if you have more of that excess reactant left over. The excess reactant then will remain unreacted and it will be present after the reaction is complete. All right, so here's an example that I have worked out for you guys. 2 moles of HF are exposed to 4.5 moles of SiO2, which is the limiting reactant. All right, so here we're given 2 amounts of a substance to start with. Now, there are 2 different approaches you can take to solving these problems. I think the second approach that I'm going to talk about is a little bit easier to see, but it does require you to do a little bit more calculating. So, it's up to you what way you want to do it, but this is what I would recommend. I'm going to show you both ways, so, whatever makes you happy. Okay, so first we balance our equation, then we figure out what our mole ratio is going to be because we're starting with moles. We're given 2 different amounts of moles, so we're going to be using that mole ratio. Now, if you look at the balanced equation, we are given amounts of both reactants. We have some amount of SiO2, we have some amount of HF to start with, and I want to know which is the limiting reactant. So one way to do this is to convert one reactant into another. That's the first method that I have shown here in the notes. If you start with the 2 moles of HF, you want to see how much SiO2 you're going to need. So based on our mole ratio, if we use all the HF that we have available, we will only need 0.5 moles of SiO2. We have 4.5 moles of SiO2 available to us. So that means that after this reaction is complete, 4 of those moles will be remaining. Okay, and that's what it says there. If all the HF is used during the reaction, we only need 0.5 moles of SiO2, so there will be 4 moles of SiO2 left over. Now, another approach that you can take is to convert both of your given amounts into the same product. And it doesn't matter which product you choose, as long as it's the same, then you can compare how much each reactant will form. So if you start with the 2 moles of HF and you convert that to moles of SiF4, that's one of our products, you will see that 2 moles of HF is going to produce 0.5 moles of SiF4. Okay, that's based on our mole ratio from our balanced equation. And that's right here. This is where I'm at. Now, if you set up the same calculation, but starting with your other given amount, 4.5 moles of SiO2, you will see that you can produce 4.5 moles of SiF4, the product that we chose. So based on this calculation, based on these 2 calculations, the first one, the HF, is limiting how much we can form. So that is what we call our limiting reactant. The limiting reactant is the one that's always going to produce less in the reaction. Okay, so here it says, looking at the calculations above, HF is only able to produce 0.5 moles of SiF4, whereas the SiO2 could produce much more than that. So that means that the HF in this case is going to be our limiting reactant. Let's see. Going on, percent yield is something else that you guys are going to have to calculate. Now, percent yield is based on 2 things, actual yield and theoretical yield. So actual yield is something that has to be given to you in a problem, or you have to find it experimentally. It's not something that you can calculate. Theoretical yield is what we call the calculated amount. So that's what you've been doing all along. You've been calculating theoretical yields from the very first day that we started stoichiometry. Actual yields, on the other hand, have to be provided for you in these types of problems. So to find percent yield, you would take the actual yield and divide it by your theoretical and then multiply that value by 100. So let's take a look at another problem here, and we're going to be calculating the limiting reactant, or we're going to be determining the limiting reactant. We're going to be calculating the theoretical yield. Now, the theoretical yield is always based on your limiting reactant. Okay, so whatever the limiting reactant is, that is what's going to tell you how much you can possibly produce, what your theoretical yield could be. So in this problem here, we're starting with 36.8 grams of C6H6, and that reacts with excess Cl2. Anytime a problem says something is in excess, there you go. That step is done for you. You don't have to figure out your limiting reactant because you know the excess is the excess reactant. And then it tells you the actual yield of one of our products here is going to be 38.8 grams. What is the percent yield? So what we have to do is figure out the theoretical yield based on these numbers and then compare it to the actual yield that's given in the problem. So we first balance our equation. It's already balanced this time, so that's easy enough. Then we set up our calculation. Here's our calculation. Starting with 36.8 grams of C6H6. That's what was given to us in the problem. We're first going to convert grams to moles because you always have to convert grams to moles. So we convert grams to moles using the molar mass of C6H6. This value comes from the periodic table. That is 6 carbons and 6 hydrogens. Add their masses together, you get 78.12 grams. Then we multiply that by our mole ratio step. And that comes from our balanced equation. And then finally, we go back to grams using the molar mass of our product this time, C6H5Cl. And so we end up with 53 grams of the product. Now, back in the original problem, it says that we actually yielded 38.8 grams. And so if we actually produce that amount, but theoretically we could have produced 53 grams, then our percent yield is 73.2%. That means that, we produced about 73% of what we could have potentially produced in this problem. So that is percent yield. All right, so that was a quick little lesson on limiting reactants, excess reactants, and percent yield, theoretical yield, actual yield, all of the new things that you're supposed to be doing this week. I'm going to do another video, a follow-up to this, by working out another limiting reactant problem for you, and it's going to be one from the worksheets that you have. Tech Chem, you have the worksheet posted on Classroom. Honors Chem, you have the worksheet in your packet. So I'm going to be doing one of those problems for you. I'm going to work it out for you, and hopefully that will help to resolve some of the questions that you guys have. All right, stay tuned.